Okay, good morning, Professor David J. De Los Reyes. It's September 9, 2023. My topic for this session will be a long video format discussion. This is alternating current machines. It's a very interesting topic, and this will now be lesson number 5. So for those of you who are following my channel on my topic AC machines, this will now be lesson number 5. Okay, let's proceed. The topic for this morning will be alternating current machines, lesson number 5. The title of the topic will be parameters relations for transformers. Meaning, parameters are actually the voltages, currents, number of turns, uh, what do you call this, impedance drops. Okay, we will be deriving the relations of those parameters. So, parameters relations, so meaning it is supposed to be in terms of an equation. Because in the design or calculation of transformers, there are equations which are needed, okay, in order for us to compute for a certain parameter. Okay, let's proceed. I will call this derivation. I know most of you are not fond of derivation, but sometimes in the study of concepts of the relations, we must have to bring out a derivation. Of course, we study algebra, okay, so actually we could formulate our equations to derive up the proper relations of the parameters. Okay, the last time around I give you the equation for taking the induced voltage on the primary and secondary. Induced voltage. Induced voltage is the voltage across this. Across number of turns number 1. That is on the primary. The voltage across this. It is actually different from the voltage applied coming from the generator side. These two here are different. There is a little bit difference because whether we like it or not, transformer, the number 1 component is actually winding, right? So for a winding, whether we like it or not, there should be a very, very small resistance, okay? And there should also be a so-called inductance. So actually, if we try to bring out the equivalent of that impedance drop, it will be R1 and X1. There is no such thing as a perfect transformer in which the internal resistance is 0 and the inductive reactance is 0. There is no such thing as a perfect inductive coil. Okay? What's next? Formula number 1, the last time around I gave you the induced voltage on the primary. The induced voltage is the voltage across this. It is different from this, right? So the one given in the formula is the voltage across the winding. Okay? It is 4.44 times the frequency times the maximum flux designated by a Greek letter P with the subscript M. This subscript M refers to maximum value times capital letter N, the total number of turns on the primary with the subscript P. So if this is primary, this should be with subscript primary. For frequency and flux, we do not put a subscript because the frequency on the primary will be the same as the frequency on the secondary. And the flux linking the number of turns on the primary and secondary are the same. So if we are talking primary or secondary, we are talking of same flux and same frequency. So that's why in equation number 1, there is no subscript here. The subscript for flux is just for the maximum value. But the important thing here is that the capital letter N, the number of turns, should be with the subscript P, meaning for primary turn. The meaning of this, the primary induced voltage should be equal to the product of this times N sub B times 10 to the minus 8. That will be equation number 1. I give you this one the last time around. It follows that on the secondary side, when current is coming in, this current passes through the coil, okay? There will be a flux circulating on the core, right? Current coming in, there should be a flux circulating here. So there will be an induced voltage on the secondary also. So on the secondary side, on this portion, current is coming in, there will be an induced voltage on the primary. Okay, it will create a flux because the two windings are linked with the iron core. And there should also be what they call this an induced voltage on the secondary across this. It is different from this because there is the so-called impedance drop R2 plus GX of 2. Formula number 2 is just actually similar to formula number 1, that is E with the subscript S, meaning S here is for the secondary, 4.44 times frequency times flux times capital letter N with the subscript S times 10 to the minus 8. So just take note of this. If this is primary, this should also be primary. If this is secondary, this should also be secondary. Okay? So to get now the relation of the parameters, we will divide equation number 1 by number 2. We will divide this point. We are performing algebraic operations, right? So this 4.44 cancel with this. This frequency here cancel with this. This flux maximum cancel with this. This 10 to the minus 8 cancel with this. So after dividing equation number 1 by number 2, okay, what will remain will just be simply E sub P, N sub P for the first equation, and E sub S over and N sub S for equation number 2. What will come out will be this. After the so-called division, it will just be simply EP over ES, and this should be equal to NP over NS. And under this study of transformer, this is actually designated as A by A. And this value here, from now on, if we see A under the study of transformer, that is the so-called transformation ratio. Okay, transformation ratio. Transformation, it sounds like a transformer, right? So when we see transformer, it will transform a certain voltage and number of turns, and that is termed to as transformation ratio. Okay, so we got relation number 1. The relation of the induced voltage on primary and secondary, number of turns primary and secondary, and that is actually equal to A. We got equation number, we call this equation number 3. Okay, so we are adding equations under the study of transformer. Equation number 1, don't forget that one, the induced voltage on the primary. Equation number 2, that is the induced voltage on the secondary. Okay, these two formulas are actually for the windings over here. Okay, due to the magnetic flux circulating on the iron core, right? There is an annotation over here. I place an annotation. At full load, no load. Capital letter I with the subscript and L, meaning no load current, is very small. Okay, compared to I sub L. What is I sub L? I sub L is the current drawn by the load. This is I sub L. This is I sub L. Oh, I no load here is here. I no load. Okay, no load meaning no load connected yet, right? So it's disconnected. So meaning to say, I place it there at full load. The no load current is very small compared to the load current. so it may be neglected. So at full load, okay, I place another equation over here. Capital AT with the subscript P should be capital AT with subscript S, meaning the ampere turns on the primary should be equal to the ampere turns of the secondary. Okay? If I no load is almost equal to 0. Okay? So from this, what is ampere turns? What is ampere? It is current, right? What is turns? It is N, capital letter N. So if we are referring to the primary side, the proper subscript should be ampere turns is the product of current times number of turns, and current is I, and number of turns is N. So the product of current times N, we place the proper subscript P, meaning the current on the primary times the number of turns on the primary should be equal to the current on the secondary times the number of turns on the secondary. And if we try to simplify this one, how could we simplify this one? NP. Oh, we just try to manipulate. Hold on. Oh, I'll place it here. For it to become NP over NS, we will divide both sides by NS, right? We will divide. So this NS cancels. This NS now is at the bottom, right? Then we will divide again by 1 over IP, both sides. So IP, NP, NS times IP, this IP here cancel with this, okay? Okay? So what remains will be, on the right side will be IS over IP. So this will be the resulting ratio. The product IP, NP equal to IS, NS, if we try to algebraically manipulate, it can be written as NP over NS, and this should be equal to IS over IP, right? Because if we try to cross multiply this, it is this, right? But this can be written as the ratio NP over NS, and this should be equal to IS over IP. But from the third equation, the ratio NP over NS, okay, the ratio NP over NS is actually EP over ES. So actually, we could combine these three equations now. Under the definition of ratio transformation, there are now three equations on how to compute for the ratio transformation under the study of transformer. First one, it will be the ratio of the primary turns over the secondary. It will be the ratio of the secondary current over the primary. It will be the ratio of the induced voltage on the primary all over the secondary. So this is now the compressed equivalent of the parameter relations. Okay? Parameter relations. So don't forget this one. As long as we are studying transformer, transformation ratio can be solved by taking the ratio NP over NS, IS over IP, and AP over AS. That's the relation of the parameters for the study of transformer. So actually, we got only three formulas. The induced voltage on the primary, secondary. This will be the third one, but this one can be placed here. So this will be the third one actually, and the third one is a long one because we got three equations. If we if we know the value of AP over ES, we could compute for the ratio transformation. And if we know the ratio of the secondary current and the primary, we could still compute for the ratio transformation. And if we know the number of turns on the primary, am I still on the camera? Okay. Over the secondary, that will still be the ratio transformation. So it seems this is a three equations, right? So three equations plus two, actually we got five equations. Okay. Okay, let's try to bring out an example problem. Example problem. Oh, at least we now know how to compute for the induced voltage here. induced voltage on the secondary. Okay, what's the other things? And the computation of the ratio of transformation in which it involves the equations. Okay, let's try to bring out an example problem. Okay. Okay, I will try to read the problem. A 2300, 230 volt, 60 cycle distribution transformer has 1200 turns on the high side meaning primary side. If the net cross-sectional area of the iron, meaning the core, is 9 square inches, if you cut the core and you get the cross-section will be something like this, and the area is 9 square inches. Right? This core area is where you want the primary and secondary windings. Right? Calculate 3. The first requirement is total flux P sub M. Number 2, the maximum flux density in the core in lines per square inches. If the area is 9 square inches, okay, what will be the flux density? Flux density is designated by letter B under the study transformer. And flux density is actually flux per unit area. That's why it's density, right? So if we could compute for the flux and we are given the area, we could compute for the flux density, right? And the last requirement, the number of turns on the secondary. We are given, it's an easy one. The given transformer distribution, you could see it on the post. It could be rated 2300 and 230, meaning this 2300 is this one. The one coming from the generator, 2300. For this transformer, the one given on the problem. And the output supposed to be, that will be, if you try to connect a load, the voltage that you could get here, okay? Neglecting losses, okay? For the meantime, we neglect losses because in the actual computations later on, we will be considering these ones. There is an effect on the, if we do not include the impedance drops. This should be X1. Right? So the given 2300 and 230, meaning this is the distribution transformer, single phase. This is 2300, the one coming from the alternator side, coming from the transmission line. And the output, if you try to connect a load over here, it's 230. So if this is 120, this is the load, the voltage we are getting from the utility line. But for this transformer, the secondary voltage is 230. Right? What's next? The primary side has 1200 turns. The number of turns here, primary, is 1200. The high side. Okay? And according to the given condition, the net cross-sectional area of the iron, the core, the one connecting the primary and secondary. If we cut this should be the cross-section. Right? And the given area is 9 square inches. So it could be 9, what's square root of 9? 3 inches by 3 inches maybe. Okay, 3 inches by 3 inches. That's where the secondary and primary windings won. Okay. What's next? That's it. The problem is asking for the total flux. Of course, if we apply a voltage here, there should be current coming in. And if there is current coming in, it will produce a flux here. P sub M. Right? There should be a flux. Okay? So the problem is asking for the flux. What's next? The maximum flux density. Flux density, it's an easy one. By definition, flux density is actually flux per unit area. So if we could compute letter A now, we divide that by 9 square inches, we could compute for the flux density. Okay, algebra, okay? We are having some unknowns involving in an equation. Okay, what's next? The number of turns on the secondary. So if the primary turns is 1,200, what will be the total number of turns on the secondary? What do you think, guys? This is a step down transformer, right? Because this is 2300 and this is only 230. So actually, you can conclude here that the value of A, the ratio of transformation is actually 2300 over 230. It is 10, right? So meaning to say, this 2300 here, since this is a step down, this 2300 should be divided by 10 for it to become 230 at the secondary side. That's the meaning of 2300 and 230. Right? Okay, let's try to bring out the solution. To bring out the solution, okay, I will erase this one so it looks good. We use equation number 1. Induced voltage on the primary, 4.44 frequency flux. This is primary, so this should be secondary terms with the subscript P times 10 to the minus 8. If we try to compute for flux, okay, guys, algebra, right? We are to compute for this. We divide both sides by 4.44 plus n sub p times 10 to the minus 8, right? So EP divided by this will be this portion here, okay? And what remains here on the right hand side, this 4.4 cancels, this frequency cancels. What's the other one? Number of turns on the primary cancels, 10 to the minus 8 cancels. So after dividing both sides by this quantity here, what remains on the right is actually the flux, the one we are solving, right? Then we try to rearrange, we put it on the left. Under the study of algebra, all unknowns, we put it on the left. Okay? All known variables will be placed on the right. So maximum flux now, designated by Greek letter P with the subscript M, will be equal to EP over 0.444 times frequency times number of turns times 10 to minus 8. I place it here, neglecting impedance drop. Assuming that for this problem R is 0, x1 is 0, okay? If there is no drop here, if we apply 2300 here, okay, EP should be equal to, B1 here should be equal to the induced voltage, neglecting R1 and X1, right? Because if we include R1 and X1, this B1 here will be different from EP. But if we try to put R1 equal to 0, X1 is equal to 0, for this problem only, okay, we could say that the applied voltage is actually equal to EP, and that will be 2300. So we are free to use 2300 using this equation here. Because if they are not the same, you could not put 2300 in here. Right? But since we assume that R1 and X1 has no effect, the applied voltage here should be equal to the induced voltage. So according to equation number 1, this EP here, you can write it as equivalent to 2300. So the maximum flux now will be capital P sub M should be 2300. We use 2300 because we neglect the effect of R1 and X1, right? So this is now a direct substitution 1 over 4.44 times 60 times 1200 times 10 to the minus 8. If you try to compute this one by using your calculator, okay, it's 7.19 times 10 to the 5th Maxwell's. The unit is Maxwell's. I think Maxwell is actually a family name, okay, of the one who discovered this flux. Okay, so Under the study of transformer, if you compute for flux, the unit is always Maxwell's. Okay? So that will be answer number 1. That's the maximum flux, okay, with this given conditions, 2300, 1200 turns, okay? And this is 230 on the secondary side. And for flux, by definition, flux density is actually flux per unit area. So if you are finding for the density of the flux over here on the core, the one that connects the primary and secondary, we will just divide 7.19 times 10 to the 5 over 9 square inches. And this is approximately 80,000 Maxwells per square inches. Okay, 80,000 Maxwells per square inches. Actually, the importance of this flux density is in the so-called design of transformers. We should know the value of B here, so you could design transformers, because for a certain area there should be a certain flux density. So if you do not know the flux density, you could not design your own transformer. Later on, we will be using this one in the design of transformers. Okay, I might discuss machine design maybe later. Oh, what's next? The number of turns on the secondary. Oh, it's an easy one. We will use the third equation here. Right? What is given in the third equation? The number of turns on the primary is given. We are looking for this. Right? E sub P is actually equivalent to B1. What is B1? The value of 2300. Right? And the value is, I put it here also, neglecting the impedance drop. If we try to neglect R2 next to on the secondary side, because the winding on the secondary side is a coil, there is no such thing as a perfect coil. But for this problem, we will neglect the effect of the resistance in inductance. So if this is 230, we could see that E sub S is equal to 230 also. So this will be 230. So from this equation, the only unknown is N sub S. So N sub S now will be NPES over EP. You try to manipulate. NS will be the product NPES divided by EP. Substituting values, the number of turns on the secondary will be 120 turns. So the number of turns on the secondary should be 120. You see the difference now? For a step-down transformer, this is 2300 and this is 230. Okay, for it to be stepped down, if the total number of turns on the secondary is 1200, on the secondary side, it's only 120. It became smaller. So this is actually a step-down transformer. Okay, step down. Okay, that's it. I think this will be a good example for tonight. We discussed the parameter relations by giving you equations 1, 2, and 3. And we applied these 3 equations back to the given problem. And there is an additional relation that was given, flux density. By definition, under the study of transformer, flux density is just flux per unit area. Okay? The flux density, how concentrated it is just the flux divided by area. That's density. Okay, that's it, guys. So the next time around, I will be discussing another topic. It's still a transformer, and it is a very interesting one. Okay, good morning from Los Angeles. This is Professor David J.